Hello, in this video I'm going to be going over a modeling differential practical situation with a differential equation, which is fairly common in the A-level specification currently. This one's from 2018, which was early on in the specification, and it's fairly typical. I think it's given us what's known as some boundary conditions. So we're going to use these when we've actually kind of like done some integrating and started solving our differential equation. It set up the variables for us in this case, which they normally will do. They're telling us n is the number of insects and t is the time in weeks. And so they've given us two boundary conditions, and we'll see why in a moment. Okay, so the information they give us is talking about a rate of increase. Now, whenever we see the word rate, that normally means, with respect to time, how something's changing with respect to time. Okay, dn by dt. Certainly in this case it does, and I think it normally always does. So dn by dt, and they're saying it's inversely proportional. So it's inversely proportional to 1 over n. You'll have seen that notation, I think, from GCSE, and you'll be used to using what's known as a constant of proportionality. So there we go. There's our equation, so there's our easy 1 mark for the first bit. So don't get much easier marks than that. Part B is to actually solve the equation and use our boundary conditions. So obviously a bit more to do. Pretty easy to separate the variables in this case to set up our boundary condition, to set up our integration because the n can just go over the other side, basically times by n on both sides, and integrate. The k can stay where it is. So we get this. And it doesn't matter, by the way, if I put a k there or put it inside the constant, the integration, because it's a constant. Okay, so here we're going to integrate that bit. That's n squared over 2. K, remember, is just a constant, so it could be any number. So that's kt plus the constant of integration. And I mentioned at the start that we've given what's called boundary conditions, and we're given two of them here. We're given when t equals to 0, n equals to 400. Okay, well, that means that we can work out one of the constants from the other one, and then the other from that information, and then we can, to work out the constant of proportionality, we'll probably end up using this a bit in a moment. So that's why we're given the two boundary conditions. Fairly common. So we can put this into our equation. 400 squared over 2 equals to k times 0 plus c. Let's rub that out. Something's gone a bit strange here. So c, that gives us c equals to 80,000. So then we can use the other boundary condition. When t equals to 1, n equals to 440. So that gives us 440 squared over 2. We could actually write our differential equation now with our c that we've worked out. In fact, let's do that, because we've got the differential equation with the c worked out is n squared over 2 equals to kt plus 80,000. But we've been given that n is equal to 440 squared when t equals to 1. So we can write that. So that gives us k equals to 440 squared divided by 2 minus 80,000. I have that number written down somewhere, hopefully. That number is equal to 16800. 16800. Okay, so we can put that back into our equation, this equation here. Now we've got k and c, so we can say n squared over 2 equals to 16800 times t plus our c, which we worked out already as 80,000. Now I can square that, and so I can double that. You can times by 2 and square root. Do it in one go. Don't need to make too much of a meal of this, I don't think. Double the constants and square root. So that's 33600t plus 16000. Okay, so I'm going to tidy up a bit, and then we're going to get on with a slightly refined and slightly more sophisticated model for the second part of the question, and then in the third part we're going to compare the two. Okay, so in the next bit they've given us the model, and because there's no constants in there, we can, there is constants, but presumably they've deliberately done this to match the t equals 1 and 440 situation, but we'll see. So we can go straight to solving the differential equation that they've given us. So to that extent it's more straightforward, but the differential equation itself is a little bit more involved. So now we've got the differential equation. We're separating the variables. Remember, n squared is that side, so we're going to be dividing that on both sides. So we might as well write that now. 1 over n squared dn. I'm going to also, you don't have to, but I'm going to take the 398 up to the top just to get so that it's not a fraction. So I'm going to take the 3988 and put it here. And that equals to, obviously the dt comes at, this is like the dt side over here. So that will become dt side, and we've got the e to the minus 0.2, the 1 over e to the 0.2t on that side. Okay, so that's separating the variables bit. And then we can let's rewrite this. You could go straight to this if you were confident. If I was doing this myself in the exam, if you like, I'd probably be confident enough to go straight to this line, but I just think if not, just don't take any unnecessary, take every steps necessary to make sure that you've got the thing down accurately. Okay, we need the negative exponent here so we can integrate it really, because otherwise it's going to make life more difficult. So again, I'm going to take this relatively slowly. This is our normal power rule for integrating. The x to the integral x to the n is x to the n plus 1 over 1 over n plus 1. So we're using that not because it's a power. So adding 1 to minus 1 is minus 2. Adding 1 to minus 2 is minus 1. And we need to divide by that number. Okay, now this, we know that e to the x integrates to e to the x plus c. But if we've got a constant, we kind of have to do this we have to adjust for the constant, reverse chain rule, or whatever we call it, is 1 over k, e to the kx. So we need to divide by the minus 0.2. And we need a constant of integration. So let's tidy that up a bit. That's minus 3988 over n. 1 over minus 0.2 is minus 5, e to the minus 0.2t plus c. Okay, so now we can use one of the boundary conditions. When t equals to 0, when t is equal to 0, n is equal to 400. Use the easy one, obviously. When t is equal to 0, n equals to 400. It's going to be a much easier one to work with. So that gives me minus 3988 over 400 equals to minus 5 e to the minus 0 plus c. So e to the minus 0 or e to the minus 0.2 times 0 is equal to 1. So that's c is equal to 5 minus 3988 over 400. And that number I've got written down also is equal to minus 4.97. Okay, so we can put that back in our differential equation. Let's just make a bit more room. So let's put it back into here. So that's minus 3988 over n equals to minus 5 e to the minus 0.2t minus 4.97. Notice actually here, all of these can be changed. They're all negative, so we might as well change all the signs to positive. And because they're positive, and that's in the front of the expression, we don't need the sign there. Okay, so they're all negative. We can change them to all positive. Now we can do the reciprocal on both sides. And that's going to be that 1 over okay, so then that is, and I can times by 3988 on both sides, and that was going to give me 3988 e to the minus 0.2t plus 4.97. Okay, so that's the 6 marks for that question, which, given the fact that it was the last question on the paper, not too bad really. So the last bit is to, this is where a bit of thought is involved, and we give it a go. We don't worry too much about. Well, obviously, we want to get these marks, and in fact, it's the whole point of modelling. We then kind of like reflect back and actually look at the two models and see which is the most appropriate. And if you look at this one, now this is going to increase. I'm not expecting you to be able to do a graph, but you could do. It's going to look a bit like that. Basically, as t increases, so model what? So this is model A, model referring to part A. As t increases, n increases basically indefinitely. It will, yeah, at a decreased rate, but it will keep going up. But if we look at model B, that there, look at this e to the, note that e to the minus 0.2 tends towards 0 as t tends towards infinity. So in other words, any large number you put into t, you can try it if you want, put 1,000 in or 10,000 in, and it gets very, very small indeed. So this is actually going to tend towards some number. There's going to be some actual, it's going to tend towards some limit here. It's going to be some kind of, it's actually going to be whatever, because this actually eventually goes towards 0 as you make t large. This one's 3988 over 4.97, which I think is about 400. And it's going to do that. So, because there's a limit to how large it will be. So this one, as t increases, or t gets large, n tends towards a value which is 3988 over 4.97. I don't think you have to, I look at the marks, I don't think you have to be specific about the values. But the point is, as t gets large, n tends towards a particular value. And if you think about it, that might be a more refined model, that might be a kind of more appropriate model, because this one implies that the number of insects will carry on and on and on forever. Okay, it might start, you increase to, when t is 10 times as much, n won't be 10 times as much, but it will be quite still significantly more. Whereas this one, as t gets really large, there's a limit to how many of these insects there'll be. That's what, so the exponential model is probably more appropriate. The question didn't expect you to say that, though. It just wanted you to kind of like notice the difference between the two different models, and it didn't expect the graph either. It's just the idea that as t increases, with this one, n increases indefinitely, whereas as t increases here, it tends towards a particular value. Okay, that's it. I hope you found the video useful, and there will be more to come. Thank you. Bye.